So first of all, thank you very much for the kind invitation. It's my pleasure to be here in Istanbul and participate in this conference. So my talk will be more theoretical. It will be mainly in two parts. One part will be related to dark energy models and how we can constrain them, and then another part related to modified gravity. So let's start with the introduction. So unlike in the previous talk in which there was a question into the cosmological principle, in my talk I will assume that the universe is homogeneous, anisotropic, on large scale. Okay? And so far the geometry is fixed, at least at large scale. And what about the matter content? So we know that only a tiny bit, about 4%, is made of baryonic matter, what we are made, and the rest is dark, either in the form of dark matter, 27%, and the rest is something that is driving our current acceleration. And this was discovered back in 27 years ago through supernova measurements. And since then, many experiments have backed up this as in the late-time acceleration of the universe. So from a phenomenological point of view, this essentially can be described through some effective fluid with an equation of states roughly of the order of -1. And well, essentially there are two ways of describing this late-time acceleration of the universe. One is by modifying the right-hand side of Einstein equation, invoking a dark energy component, which can be on the form of scalar field, of a perfect fluid, plenty of possibilities. And also, depending if they fulfill or not the null energy condition, it could be of the type quintessence or of the type of a phantom fluid. Now, the other possibility is that gravity at larger scale modified from GR. And there are also plenty of ways of modifying gravity. Some of them are mentioned there. One of them is essentially assuming that we have a metric and a connection, and the connection doesn't need to be the Christopher symbol of the metric. That's the Palatini approach. We can also invoke non-torsion, so essentially the connection will be antisymmetric. We'll have an antisymmetric part, and many other things like non-metricity, which is the case that I will discuss on the second part of my talk. Now, if it's the simplest case is a cosmological concept, we know that this could drive some issues like the coincidence problem or the initial condition problem. And why now? Why we have exactly now more or less the same percentage of dark matter and dark energy. Also the scale, why is it so low? And the several tension we have heard on this conference. So in my talk, what I will try to address is the question I raised there. So how can we, through some several theories, either in the context of dark energy or modified gravity, try to address some of these issues? And plenty of them have been addressed on the review by Eleanor and Jackson et al. Okay, so my first part will be related, as I said, to dark energy, and I will start with some scalar field, in particular with the quintessential model. So in this quintessential model, so essentially this is the Lagrangian, so we have a minimum coupled scalar field with a potential. And usually these kind of models, they help to sort out the coincidence problem, although not so much the H0 S8 tension. So the potential I will assume is a generalized axion-like potential of this form. So when this exponent is exactly 1, this is what have been used for wave dark matter, where essentially the mass of the axion of the order 10 to -2 eV. Now, it has been also used for early dark energy, and here I will assume it as a model for late dark energy. So in this case, we will assume that this exponent is negative, or equally that this n is positive. So this potential has a minimum rather than having a maximum, okay? That could drive some de Sitter expansion. And this is based on a work done with Carlos García Boiza, one of my PhD students, and Huan Xian, a postdoc in China. And so to analyze this kind of model, it's quite useful to use a dynamical system approach, where essentially the scalar field will have 3 degrees. One is related to its kinetic energy, one is related to its potential, and then the slope. So as soon as we move away from an exponential potential, we need to take into account that parameter. And we can define an autonomous closed system this way, so I don't want to bother you too much with the equation, but essentially, in the dynamical system, we look for what are the solution that gives 0 on this right-hand side, and then we study the stability. So in this type of model, for the model I showed before, which is essentially kind of potential of this shape, so there are 2 saddle points. One is radiation back in the past, then a matter, dominated universe, and then finally we would have the theta asymptotically in the future whenever n is positive. Okay? So this is what happened. And in particular, this kind of model, they are attractive because they can have a tracking behavior. What does this mean, essentially? So this means that at some point during the evolution of the scalar field, no matter the initial condition we impose, we will get essentially the same behavior. So the dependence on the solution on the initial condition will be somehow lost. And in particular, in this kind of model, whenever this parameter gamma, which is related to the concavity of the potential, is larger than larger than 1 and almost constant, while lambda, which is related to the slope of the potential, is quite large, we can have tracking behavior for the scalar field, whose equation of state would be this one. Okay? So let me be more specific. So first of all, the potential that we have considered are of this shape. So n is positive. So essentially, they have a minimum. Okay? And then depending on the value acquired by n, they can be narrower or wider. Okay? And the tracking regime, we can find it on this region when the scalar field is somewhere over here, where we have the parameter lambda quite large, as can be seen here on the plots, and the parameter eta is almost a constant. I will show it in a moment. So close to the minimum, the potential can be, as I said, approximated by this expression. This minimum would be over here, and then it will have a mass. The mass will depend, of course, on the scale set by lambda, by this parameter here, and also on the ratio between n and eta square. So the larger is n over eta square, the larger is the mass, and the scalar field will roll faster. So, as I said, the tracking regime would be, would be here, on this area here. So essentially what happened, the scalar field will go through a frozen regime, in which essentially its kinetic energy is subdominant, and then it will reach the tracking regime, in which no matter which are the initial conditions, all the lines will come to these parts. And then later, the equation of state will reach -1. This plateau, this value over here, will depend on the value acquired by n, okay? Now, what happened with the matter power spectrum is the following. All this from a theoretical point of view. I will show in a moment what happened with the, when we do the fits. So if we set n equal 1, which means, let me go backward. So if n is equal 1, in this case, what we have is that on the tracking regime, this effective equation of state, it's of the order minus 0.5. If we take n equal 0.1, then this effective equation of state will be smaller. In fact, the smaller or the closer n is to 0, the closer we are from lambda CDN. And in that particular case in which n is exactly 0, so what we would have is exactly lambda CDN. So for this number, so this would be the matter power spectrum. Here we have ignored the baryonic acoustic oscillation, resolving numerically the equation. This is the case n equal 1, and this is the case n equal 0.2. Okay? The same thing, we can do it by looking at the F sigma 8 distribution, and this is what would happen for n equal 1, okay? And this is n equals 0.1. As I said, so far here we haven't done any fits, it's just a theoretical approach. Now let's see what happened once we carry the fits of this model. Let me remind you how many free parameters we have here for doing the fit. So essentially what we do is the following. So for our MCMC simulation, so what we did was we start on the frozen regime, so that phi dot we can set it to 0. So what are the other parameters that will be left? So the initial value of phi, the potential, which is essentially lambda, and then also n, and eta, which makes essentially the mass of the axion in this axion-like model. Okay. And what we did was essentially we considered a few data sets, starting from Pantheon Plus and Rees et al., which is the green one over here on these plots. Then this first year, which are the gray one. And the reddish one, this tiny one over here, is Planck 18 and Deci Bao. And then finally, the blue one are the combined one. So the fit is essentially similar to lambda CDM. The value we get for H0, for omega m and S8 are similar to S8. So what do we gain with this kind of model if we are getting the same thing? So essentially the question of problem. No matter what are the initial conditions, we will have something nowadays that resemble a cosmological constant. So if we compare it with lambda CDM, which is what is done here, so this is the same plot we had before, and this is for lambda CDM. So the value we get for H0 here and here, they are pretty much similar. The same thing happens for omega m and for S8. So our statistical analysis for when comparing this model with lambda CDM is shown over here. And as you can see, so the numbers are pretty, maybe you cannot see it's too small, but anyway, I can tell you these numbers are close to 0. So essentially, there is no preference between the two models, and we cannot rule this axion-like potential. The other thing I wanted to highlight is that, as I said before, the values we get for H0, CMB alone, are pretty much similar in both models. The same thing when we add Bao, supernova, Lord Z, and Deci. And here, essentially, what we are comparing is the tension that we have between the different data sets. So when comparing our model with Bao data with CMB, so the tension is slightly larger as compared with lambda CDM, but when we add supernova, the tension is slightly smaller, slightly. In the other case, we got 7 something, and here we have 6 something. Now, the tracking regime that I was mentioning before, we can see it on our MC. So this is just for the CMB case, and this is for the CMB on Bao. So you can see that the scalar field, it starts on the frozen regime here, then it reaches the tracking regime, so this is the equation of state of the scalar field versus the scale factor, today, the past, okay? When we add Bao, so essentially this tracking regime happens at the W effective, which is slightly smaller, okay? Now, the evolution for the different energy densities, the standard one. And then here, we are not doing a fit with the redshift space displacement. Here, we are just plotting the several realizations that we have for the MCMCs, and on top of it, the error bar. Currently, we are doing the fit of this model with the redshift space distortion. Okay. For the CMB, it's essentially the same as what happened with the lambda CDM model. Okay. So let me move to another type of model I would like to speak about, which is the kinetic gravity braiding model. So in this case, instead of having a minimally-coupled scalar field with a given potential than the one we discussed before, it's something more general. So kinetic gravity braiding model were proposed by Cédric Defayet, Bujolas, Sawick, and Wickman back in 2010. And those are a generalization of K-sense model. So essentially now, this function is an arbitrary function of the scalar field, and X, which is the kinetic energy. And then there is another term, which is this term over here, where there is a coupling between it's a function of the scalar field and the kinetic energy, which is coupled to the Laplacian of the potential. These are the only two terms that survive from the Hornitsky type of theory after applying the constraints on the gravitational waves. So essentially, we have a mixing over here between different degrees. This kind of solution is known to have the theta attractor, okay? And in particular, it's known that we can have phantom behavior without ghost or gradient instability in this type of model. What I'm saying is subdominant on the sense that what happens is that the equation of state of the scalar field can mimic a phantom behavior. This doesn't mean that H dot is a growing function. So in that sense, I'm putting here subdominance. So the work we did with Theodor Borislavova and Prado Martin Moruno, both of them from the Complutense University, and Theodor just finished his PhD recently. So what we did was asking the question, can we have this kind of behavior, phantom again, but which is a true phantom behavior in the sense that H dot asymptotically would grow, okay, and keeping these no ghost and no gradient instabilities. Okay? And for simplicity, we will assume the shift symmetric case, which means essentially these terms do not depend on phi. Or said in another way, they are invariant under the translation of the scalar field. Okay? So in this kind of model, because they are quite involved, the Friedman equation is very important to look at the symmetries, and in particular, it can be shown that they have a conserved shift symmetry, which is given through this current. So this term over here, no matter what is your k and your j, will decay like 1/8 to the cube. And usually in the literature, this term was set to 0. But if you don't set it to 0, you can get many more solutions. That's what we did. Okay? And the energy density is conserved, of course, because the different streams invariance is preserved in this type of series. So this would be the Friedman equation, this would be the Ricciarduri equation. So to look at the model, it's simpler, again, to do a dynamical system analysis, defining in the usual way the radiation components and the matter components, okay? These two parameters, they are bounded between 0 and 1. Now, for the scalar field, one extend the expression we showed before for the minimal coupled scalar field, okay? Now, because we were looking for a solution in which h dot could grow, and therefore h could get very large, it was convenient as well to introduce a new variable, this small h, which is a compactification of the Hubble rate, in case if we have solution of the type of big rip or sudden singularity and so forth. And then, of course, the Friedman constraint is essentially written here. So by doing so, the analysis, so essentially we need to look again when these equations are equal to 0. This is essentially the Hubble rate, the energy density related to radiation, and the scalar field. And there is a very simple way in expressing, and very intuitive from a physical point of view, which is by introducing this parameter C1. So when C1 is positive, so what happens is that the solution will be such that h grows on time. So we will have effectively a phantom behavior. On the other hand, from the geometrical point of view, on the other hand, if this C2 is positive, then what happens is that this equation of state of the scalar field is smaller than -1. So the phantom will be associated to that scalar field, not the geometry as a whole. And it can be seen in general that is in this kind of theory, there are 5 types of solution. One of them is dominated by matter or the scalar field in such a way that asymptotically what you have is a Minkowski. Then you can have solution that behaves like radiation in the sense that the effective equation of state is 1/3, and it can be for the type of scaling solution. Then, of course, we have cosmological singularity, in particular Big Bang in the past, which would be radiation dominated, but you can have also other singularity in the future, as I will show in a moment, which is a big rip singularity. And of course, the theta solution that were known already on this kind of model. So here, all what I wanted to highlight on this table is the points, this one over here. So this was the attractor that was known before in the literature, and this is the new attractor that we found, is the big freeze and the big rip. This is so for this simple model in which we have set k equal to 0, and the coupling j is an exponential function of x. We analyze other models, but here for the presentation, I'm just showing this case. We also found other type of solution, like a sudden singularities. Okay, so those are all singularities that could happen in phantom dark energy models. Okay, so this is from the background point of view. So essentially, in this type of model, in particular, when we go back, when beta, okay, is between -1/2 and -1/4, so we can have this big rip. And the evolution of the universe in this type of model is such that in the past we will have a Big Bang driven by radiation, then we will have a matter-dominated point. We are currently somewhere around here, and then boom, this would be in the future, a big rip. So these kind of solutions were not previously studied in the literature. And the evolution for the different background quantities is the standard one. Now, is this model stable or not? That's the point. So unfortunately, at the background level, everything looked okay. So we had this phantom-like behavior. But then when we looked at the perturbation first order, what happened that no matter which way for all the model we have looked at, so essentially you have a tachyonic instability or a ghost instability. The tachyonic one is quite bad because essentially what happens is for a given mode, when you look at the perturbation, this perturbation can grow, and that can take place during the structure formation, and that's why the model would be unstable. For the ghost, it's not a problem. is not a problem as strong as with the tachyonic instability, because there are way out from that problem. The other issue is that in this type of models, if you look at second-order perturbation, essentially the scalar field perturbation are feeding some overproduction of an overproduction of gravitational waves. Okay, so given all these issues, so in this case we didn't do the fit of the model, although from matter of curiosity, I wonder what happened at the background level at least, if the model is good or not. And the third example I wanted to speak about in the context of scalar field, now it's not a scalar field, it's essentially a three form. It's another way of describing dark energy. So first of all, what are these three forms? So they have been in the literature for a while. So back in the 80s, they were using supergravity and also in string theory, and they were a way of tackling back in the 90s the cosmological constant problem, because essentially a three form in absence of a potential, it behaves exactly as a cosmological constant. It had been used also in inflation, okay, and also in dark energy. So what are these P form in general? So P form is an antisymmetric tensor, okay, and its degrees of freedom depend on the space-time dimensionality, and if it's a P form, a 3 form, a 2 form, and so forth. So if we are in 4D, in 4 dimensions, so we can have 4 types of P forms. P0 is essentially scalar field, like the phi we had before. We can have also a vector. If it's a vector, it's a 1 form. We can have P2, which is essentially 2 form, and then we can have P equals 3, which is a 3 form that I will talk about. And this case and this one are the simplest one because they have only 1 degree of freedom. Okay, so they can play the role of dark energy, as I will show in a moment. Okay, so the action to describe this 3 form is the following: the gravitational action. So this is a potential which has to depend on the square of the 3 form, and this is the kinetic energy. So F is the 4 form, which is essentially the exterior derivative of the 3 form, and this would be the equation of motion of the 3 form. So what happened is that in absence of a potential, this is 0. Therefore, this is 0, which essentially implies that this part over here is a constant, and therefore they mimic a cosmological constant in absence of a potential. Okay? So massless 3 form is equivalent to a cosmological constant. Now, if we are in a Friedmann-Lemaitre-Robertson-Walker, the only degrees of freedom that has the 3 form is the one that we get when we have the 3 components corresponding to special components. And that degrees of freedom is encoded on this function, is chi of t. Okay? So how does the Friedmann equation looks like in this type of model? So it's modified with respect to a scalar field by this term. So this would be the kinetic term, and this is the potential term. Okay? So this term modified evolution with respect to a minimally coupled scalar field. Now, for the Ricciardo equation, what we have is the following over here. So depending on how does the potential behave with the 3 form or with the square of the 3 form, so if it's a growing function, so what happens is that what we will have is that h dot is always negative, while if it's this side is negative, which means essentially that the potential decay with the square of the 3 form, what we will have is a phantom-like behavior. And this phantom-like behavior happens even though what we have on the action is the standard sign here. So we haven't flipped the sign of the kinetic term. And this would be the evolution for the equation of motion of the 3 form. Okay. In particular, we will have one extra critical point with respect to the case of a scalar field, which is when chi equal to chi c. I will show it in a moment what does this mean graphically. So we can have 2 types of potential. So either the potential is a growing function of the square of the 3 form, or it is a decaying function of the square of the 3 form. So in this case, what happened is essentially that h dot is always negative. While in this case, what happened is that h dot can be positive. So in this case, we can have phantom behavior. Oops, here. In this case, we can have phantom behavior. In this case, we don't have phantom behavior. And in particular, what happened is that essentially the 3 form will roll up the potential. Depending on the initial condition, it might reach the top and then rolls this side, or otherwise it will go back. And this will be the attractor, this line over here, or this line over here, depending on the initial kinetic energy that the three-form has. And these points over here, this one here, and this one here, will correspond to what is known as the little signal of the big rip. It's a milder version of a big rip singularity. Okay, so what we did is essentially to analyze this type of model from an observational point of view. But let me show you briefly what happened within the dynamical system approach. So what happened essentially, the universe would start here. We'll start at a matter-dominated universe. It will reach this green point, which is essentially a kind of the theta, and then head to these red points, which is the little signal of the big rip. So that's what happened in this for a Gaussian potential, okay, in which we can have a phantom-like behavior. So currently with Carlos García Boiza and Su and Xian, we did the same thing that we did with the axion-like potential. So essentially, we used, we did the fit using the same data. So Pantheon plus and Ries, the green one. The gray one, this first year. The red one, Planck, 18 decibel. And then the blue one is the combined one. There is a difference with respect to the previous case. On this case, with respect to the axion-like potential, on this case, what happened is that our H0 values, okay, for the three-form is slightly larger. And that could help to alleviate, not solve, but to alleviate the H0 tension. For S8, what we have is the opposite behavior. So this would be the case for lambda CDM, and this is the three-form case, okay? In the case, as I said, we get a slightly larger values of H0. And these are different realizations, so what happened essentially, the three-form starts back at large value, okay, on the right-hand side of the Gaussian potential, and then it starts rolling up, okay? Depending on the kinetic energy, there are a few realizations in which they cross the top of the potential, and nowadays they are on the other side. But most of the MCMC realization, the three-form is still climbing the potential, the three-form potential. And the equation of states, so back in the past, would be, sometimes it's not easy to handle this pointer. Okay, it will be close to -1, which means when we are at the tail of the potential, then it will decrease, and then again asymptotically, well, asymptotically no, present it will approach again -1. And these few lines over here are the one corresponding to this one here, okay? Which is essentially the realization in which the three-form has reached the top of the Gaussian and then is on the other side. But those are, as I said, minimal realization. And this is, again, for the behavior of F sigma 8s, okay? So this is just a representation of the different realization. Again, we are currently doing the fits, including red space distortion, which was not done here. The only data that were used is the one I showed on the previous slide. And as what I wanted to highlight is that this value for H0, maybe you cannot see them, these for lambda CDM, are slightly, for the three-form are larger, okay? This one over here, as we compare those coming from here, okay? And the fit is slightly better for this three-form as compared with lambda CDM. Okay. Let me move to the second part. As I don't have, how many minutes do I have still? 6. Okay. The modified gravity part. I will try to be quick. So, as I said, my talk is divided in 2 parts. One was tackling with the studying dark energy model and doing the fit of this model, and now we move to the second part, which is modified gravity. There is a whole zoo of modified theory of gravity. I will stick just to F of Q gravity. So I will assume from now on that our space-time has a metric as before and a connection, but that connection does not need to be the existence of a symbol that I assumed on the previous part of the talk. And in particular, I assume there is no torsion. So this connection will be symmetric on the index mu and nu. So metric compatibility means this, for the kind of theory that I will assume, so this term of the covariant derivative of the metric will be different from 0, okay? And the connection is symmetric. What this means essentially is that when we teletransport a vector, the length of that vector can change, okay? Now, we have a connection and we have a metric, so the curvature of this given connection can be always decomposed into a term which is related to the scalar curvature of the Levitch-Vita connection. Thank you. And then another term which is essentially the scalar non-metricity scalar, which is all this thing here, plus some surface. Oops. Plus. No. Plus some surface term, okay? So what happened is that if we are in a theory where this term here vanish, and now our action is linear either on this term or on this term, the theories are equivalent. So I can get GR essentially by considering this term or by considering this term, because, as I said, the action is linear. Now, however, if what I have is an arbitrary function of the curvature defined through the Christoffel symbol, that theory isn't different from an F constructed from here. And this is due to the surface term. So now we have to be careful. That's why F of Q in general is different from F of R. And these, of course, give a whole bunch of possibilities to analyze. And this theory was proposed by José Beltrán, Levin Heisenberg, and Tommy Koivisto back in 2018. This is the action. So to get essentially the equation of motion, we need essentially to vary the action with respect to the metric and the connection. And again, the energy momentum tensor in this type of theories is conserved. Okay. So again, I will assume a Friedmann-Lemaitre-Robertson-Walker universe. And when getting the equation, one has to be careful, because essentially one needs to impose the flatness condition, essentially the scalar curvature of the connection is 0, and at the same time that the symmetric connection fulfills all the symmetries of the system. And in general, there are 3 possible connections. Here I will choose the simplest one, and which means essentially the simplest choice for the connection preserving the Friedmann-Lemaitre-Robertson-Walker written on the standard way, this one over here. Recently with Ismael Ayuso and Kostas, who is also here, we have analyzed in a more theoretical setup some models. But as I said, here I will just focus on the simplest case in which our metric can be written as a Friedmann-Lemaitre-Robertson-Walker with the simplest connection. In that case, the Friedmann equation is the one over here, and this would be the Ricciardo equation. As I said before, the matter, the energy density is conserved in this type of theories. Okay? And we have analyzed 3 models with Manos Saridakis, with Carlos García Boiza, and one of the students of Manos, Maria. And these are the 3 models we analyzed, okay? F1, F2, and F3. All these models give rise to latent acceleration in the late universe. So that's the reason why we look at them. So how do these functions look like? So all the functions asymptotically in the past, they are linear in Q, which means essentially that we recover GR in the past. So we have no problem with Big Bang nucleosynthesis in this type of model. How about the effective gravitational constants, which is what is drawn here? So this is the effective gravitational constants versus Q. So this is the past, this is the present. This is the past, this is the present. So for 2 of the model, what happened is that the effective gravitational constant for model 1 and 3 grows, while for model 2, it decreases. And this will have an effect when doing the fit of S8. So the set of data we analyzed, we consider in this case, so the first combination consists of cosmic chronometer, supernova, and gamma ray burst. On the second combination, we assume baryon acoustic oscillation, bow, and redshift space distortion. And finally, on the third set, we combine them. So what we got is the following. So if we consider only local measurement, so what happened is essentially that model 2 prefer a lower value for omega m, while model 1 and 3 a larger value of omega m. When we add redshift space distortion and bow data, what happened is essentially that model 2 prefer a larger value for S8, while model 1 and 3 prefer a lower value of S8. And finally, by combining all the data, so what we got is what is shown here. So for one of the cases, essentially two of the models, they prefer a lower value for H0, which help to reduce the H0 tension, while for the second one, what we have is a larger value for S8. But this comes at a cost, and the cost is essentially that there is, let me go to this, and then I will go back. So there is a tension with the different data sets for the value of omega m, okay? So what we are currently doing is a following approach that was implemented by Ismail Ayuso, Rus Laskos, and I forgot now his name, the third one. Enzo, I forgot his family name, I should have. And we are adding a cosmological constant, and on this fit it seems like what they did, so we can keep the good side of the 3 model while at the same time improving this number over here. So it seems that it's something intrinsic to these f of q theories. Okay, so let me conclude. So essentially in this talk, as I said, I mentioned 2 sets of models. One of them is related to dark energy, and the second set is related to modified gravity. So in particular, we have introduced an axion-like model that mimic a dynamical cosmological constant through a tracking regime. The fits are essentially as good as for lambda CDM. Then we have described the dark energy through a kinetic gravity braiding model or a 3-form. And the 3-form with the Gaussian potential seems to point to an alleviation of the H0 tension. Then we have analyzed several f of q, and in particular we have highlighted the effects of the effective gravitational constant on the value obtained for S8. And in 2 of the models, it seems that the tension in H0 can be released. Currently, we are analyzing some extension of the model proposed by Osgur and collaborator, in particular with Alberto Vázquez, which is the lambda S cold dark matter, in which you have a transition from a negative to a positive cosmological constant, and this is done with Beñat Ibarra, another of my PhD students at the University of the Basque Country. So we are trying to analyze what happens if this transition is smooth. The theoretical model have been already posted on arXiv. You can find them here. We are currently doing the fits, and the first fit seems to be, the initial fit seems to be promising. Then in a different work we are analyzing with Benetti, Paloma Morillo, and Salvatore Capotiello some extension of modified general sharp-Ising gas. And why this extension? Because the modified general sharp-Ising is quite chameleonic, on the sense it can behave in many, many ways. And in particular, it can encode most of the dark energy singularities. So what we are picking is different cases that would lead to different singularities and see what happens, how suitable they are from an observational point of view. And we hope on the coming months, the coming weeks, we can post the paper. Okay, so that's it. Thank you for your attention. Sorry, I took 3 minutes more.
Thank you, Mariam. Okay, questions?
Yes. Very nice talk. I would like just to, just a curiosity. In the model that you presented for FQ gravity, yes, how you can distinguish with respect to similar models that we have in FT gravity?
In?
FT.
It's something, is the next thing. So the next step is to do the same thing with this kind of model. I don't have an answer right now.
But you have some difference in the profile. You suspect you have a difference in the profiles.
You told me f of t, right?
Yeah, FT.
Yes. The 3 models we analyze are this one, okay? One of the things that we are planning is to do the same thing, but instead of f of q, f of t.
Okay.
But as you know, although t behaves essentially as h squared, the Friedman and Raychaudhuri equation are different, so I cannot, because these 2 will be different. Or even though if t goes essentially as h squared.
So the Raychaudhuri is the difference?
Yeah.
Okay, yeah. Thank you.
Okay, thanks for the talk. I have 2 questions actually. The first one is about this axion-like model.
Yes.
For that model, isn't it more physical to consider the coupling of phi term, not only with the potential, but to FF tilde type of electromagnetic field for the axion-like potential? Because this potential actually will be created through that type of coupling of scalar field, axion, for example.
So what you are saying is that to have not only a V.
No, it's not that model actually. Axion-like.
The axion-like,
Yes,
sorry,
axion-like
yes,
potential.
yes, yeah. Yeah, here is just a quintessence model, so we didn't assume any coupling. Yes.
Yes, the potential here is really axion-like, but on the other hand, if it is axion-like, I mean, it should be also considered the effect of this phi here to coupling of its to electromagnetic field. Well, there is a usual suspect for this electromagnetic field, it's the CMB. And even for this small coupling, kind of things may help in the context of this model, of course, to alleviate, for example, the H0 tension or something like that.
Yes. Thank you for your suggestion. We didn't take into account those kind of coupling. I stressed here that this is not an axion, that's why I put here an axion-like, okay? Because
yes.
it's not exactly the shape of a, but this kind of coupling, we didn't take them into account. And in fact, when doing the fit, because we have too many parameters, we started the fitting when the scalar field was frozen, so that we decrease 1 degree of light. Now, if we add a coupling, I don't know for the fit how long it would take us. Okay. But anyway, we can speak later on. Thank you for your suggestion.
So my second question is about the origin of the tree-form field.
Here. Well, it's essentially phenomenological and my imagination also.
Yes, because
there is no.
Well, these tree-form fields appear in string theory like solitonic objects in,
yes.
I mean, the
so,
Neuer-Schwarz sector especially,
yes.
but not as an only tree-form field kind of thing.
Yeah,
there are also some additions.
Yes. So first of all, when they appear in string theory and also in supergravity, usually they are not on a Lorentzian spacetime. They are in a Euclidean spacetime. Okay, that's the first thing. Now, given that they have been used, as I said, in inflation and also for the cosmological constant, what we did was just an extension, modifying the potential. But yes, when in this context, yes, I have to agree that they live on an Euclidean spacetime, not like the one we are using here. So what we did is an extension of the phenomenology that was carried here and here. So that's what we did. And then the thing is that when we started looking at this kind of model, what attracted my attention was this, okay? So if I play around with the potential from a phenomenological point of view, that's it. No, it's not, I cannot say if there is a true fundamental reason for using this potential, then depending on the behavior that the potential has, we can have a quintessence-like behavior or phantom-like behavior.
Well, but then in that case, I mean, coupling of scalar field to FF tilde of electromagnetic field may produce an effect of this tree-form field, actually.
Yeah, if we couple it to
yes.
F mu, yes, of course.
Okay, so let's thank Mariam again.